Yeah. Uh, Good evening, one and all, and welcoming you to the third live session for the course Production Technology Theory and Practice. So it's an NPTEL course. The tutor for this course is Professor Shaunak Kumar Chaudhary from IIT Kanpur, and I, Arnav, am the TA for this particular cycle of NPTEL. Expecting that you have gone through the lecture videos for the last week, I have framed a few questions and I want you all to participate actively in discussing the doubts related to the question and also solve the questions. Okay. So, I think the first question is visible to you all, right? Hello? Any yes, no, anything? Nikhil, can you see the first question? Tawfiq, you're there?
Yes.
Yeah. So, yeah, you can keep yourself unmuted so we can discuss, right? So the thing is, in the last week, we have seen what is the relationship between the true stress and the engineering stress, and how the, the stress strain curve differs for the engineering stress, engineering strain. If we move from engineering stress, engineering strain domain to true strain domain. So for tensile test, we have seen this is sigma and epsilon. If this was the curve for engineering stress, engineering strain, then for true stress, true strain, it would be somewhat like this. So if this is the ultimate tensile strength point, then somewhere here we will get the maximum force or the maximum load point for true strength, true, true stress, true strain curve. So in this question, they're telling that the ultimate tensile strength of a material is 400 MPa, megapascal, and the elongation up to a maximum load is 35%. We know that the material obeys power law of strain hardening, which can be written in the form of sigma equal to k into epsilon power n. Then which of the following correctly depicts the true stress true strain relationship? So basically, we are being asked to calculate the value of k and n. So that's the question here. Now we need to we will approach this problem in a few steps. So the first step would be to identify what is sigma and epsilon here. So these are the true stress, true strain. Like it is not engineering stress, engineering strain. Rather, this is true stress, true strain. Okay. The ultimate tensile strength of the material 400 MPa, that is actually the engineering strain. This one. Okay. So we need to get the corresponding value here. So for that, what we will do, we will convert this engineering stress to true stress. The equivalent true stress is of the following relationship: 1 plus epsilon. Okay, and this is also like engineering strain. So this is 400 MPa at the maximum tensile strength at this point, and This is 0.35. From 35%, we get 0.35. So what will be this value? Talking, what will be this value of sigma t? Just calculate and let me know. It's 540. Okay, so this was the first step to the problem. Similarly, we can also find out epsilon t. It's ln1 plus ln e. So it will be ln 1.35, which is approximately 0.3, rounding up to 3 decimal places. Yeah. Yeah. So we have calculated the true stress and the true strain from here. Now we know that this and this will satisfy this particular equation, right? But see, we know here the unknowns are k and n, but we know the value of sigma and epsilon only at one point, that is qts. So we need another information, or say another point along this particular curve to predict to know the value of k and n, but we don't have that value. But if you have gone through the basics of plastic deformation, that is in this regime, then you would have come across this particular information that at maximum load, in this case that UTS, we can conveniently derive that this strain hardening exponent n is equal to the true strain at that particular point. So this is my true strain 0.3. So we can write that the value of n is equal to epsilon at the maximum like loading point. So this derivation this derivation is a small one, so I will derive it in the next slide. But this information you need to remember. So the strain that you encounter at the maximum loading point, that is equal to the strain hardening exponent. Now the problem becomes easy. So now you can directly write n is equal to 0.3, because this is the maximum point. Maximum means the maximum at the engineering stress, engineering strain curve, not at the true strain curve. It is the maximum loading point here, the ultimate tensile strain, that point I'm talking about. So we can write n is equal to 0.3. So substituting the value here in this particular equation, we will get 540 is equal to k into 0.3 to the power 0.3. So from this we will calculate k. It's coming around 774.90. So which option is it matching? We have option B here, this one. So it's approximately equal to 775 ampere. Hence it's option B. Okay, this type of numericals you can expect in GATE and other competitive examinations, and also in like NSEM exams. And now let us derive this particular this thing that I just said, that n is equal to the strain that you encounter at the maximum loading point. How we are arriving at this particular information? So yeah, mm, we can write sigma, which is the from now onwards I am denoting this sigma as the true stress. Okay, not the engineering stress, and similarly epsilon as the true strain. So we can write F by A. So these are instantaneous values. The force, it's obviously instantaneous. Sorry. Yeah. This A area, that is also instantaneous area, right? So we need to find out epsilon at maximum load, F max. So dF by the epsilon equal to d by d epsilon of sigma into A. Okay. So as we are straining the material, both sigma and A is getting varied, right? Sigma is also increasing, the true stress, and the area is also changing. Here area means the area of cross section of the loaded material. So we can write here, right? So I am tagging it as equation 1. Okay. Now another thing, during plastic deformation, we can assume that the volume of the material is constant. As the material is straining, its length is increasing, the area of cross section is decreasing. So we can say under tensile load, yeah, under tensile load, this length is increasing, area of cross section is decreasing, but the total volume of the material is remain constant. This will happen till the necking begins. At the onset of necking phenomena, the voids will will start appearing across the cross section, and due to these voids, then the voids will try to coalesce with each other, and as a result, the cross section will decrease drastically. But before the necking region, we can write that the volume of the material is constant. So volume can be written as A into L. However, this A and L is changing. This A and L is changing with time, but the volume is constant. So we can also write del V by del E is equal to 0, right? So that's nothing but, sorry, dV by dt. So d by dE d epsilon of AL is equal to 0. So that's A into del L by del E plus L into del A by del E is equal to 0. Okay. So, okay, another thing, we know that the instantaneous strain is equal to dl by L. So L is the instantaneous length of the material, say at time t is equal to t naught, and del L is the change in length from t is equal to t naught to t is equal to t naught plus dt. Okay, so this much change is occurring in time dt. So the strain that is being imparted in the material is del L by or dl by L. Okay, so we can write del L by del E is equal to L. So we will substitute it here, and what we will get, A into L plus L to del A by del epsilon is equal to 0. So L will cancel out. So del A by del epsilon is equal to minus A. So we have got this information from here. Now the problem has become easy. We need to substitute this one into equation 1. So upon doing that, what we will get? So I'm writing it here. Epsilon into this one, we have got minus A plus A into del sigma by del epsilon is equal to how much? It should be equal to 0 if we are taking this derivative at f equal to f max, right? So del f by del epsilon at f equal to f max will be nothing but 0, right? Because it's a maxima there. Okay, so here also a will cancel. Then del epsilon by epsilon will become, sorry, del sigma by sigma will become epsilon. So yeah, now we also know this relationship, right, for two stress and two strain. This is the power law, and if you know that the material obeys this particular power law, then we can differentiate this particular equation and write this. Okay. It's better to keep it in the original form itself. Now we will just substitute this value again in this equation. So sigma is equal to k into n into epsilon n minus 1. So again sigma we can write as k into epsilon power n, which is equal to k into n into epsilon power n divided by epsilon. So here we see that kk is getting cancelled out, epsilon power n cancelled out. We are left with n is equal to epsilon, right? So this is the particular expression that we used in the above numerical here. And you have to note that this epsilon is the strain at the maximum loading point. That is f is f max. So if you look at your engineering stress, engineering strain curve, this particular red one, you can see that the material is getting loaded till here. After this, even if you don't increase the load, the material will start nicking. At constant load, it will start nicking, and its area of cross section will decrease further. So this is that maximum loading point. In this particular problem, this particular value is nothing but 0.35, and this is 400. And similarly, this particular value is 540, and this one is 0.3, as we have calculated. So yeah, that's it. I think you have understood this derivation. If you haven't, please come up with your questions. We can. I will try to solve your doubts. Do you have any question here till this particular problem? I hope that you have understood this. Okay, thank you. So you don't have a problem, right? Yeah. Okay. Moving on to the next question. So last week's videos were mostly related to machining process, like mostly turning. So the first problem that we discussed is from previous week. Yeah, now we are starting this week's assignment problems. So, sorry, last week's assignment problem. So, a tool is specified in the orthogonal rate system as follows. So, in orthogonal rate system, what is the unit of the, what is this first of all, what is this? What is this 0.5? I hope that you are familiar with the tool signature in different systems like ASA, ORS, NRS, MRS. So what is this 0.5? It's the nose radius, right? It's in mm. Although this information won't be required in this particular problem, but still I am trying to get you familiar with this small points. Okay, and the other angles, you can unmute yourselves and tell, like, what is 5 degree here in ORS system? Any answers? What is 5 degree? So this is the inclination angle. This is the orthogonal rake angle. This is the flank angle in the orthogonal plane. The principal flank angle in the orthogonal plane. This is the this is the principal cutting edges. You have two cutting edge for a given tool, right? This is the principal cutting edge. This is the auxiliary cutting edge. So, say at this particular point, we are trying to visualize the tool. So in ORS, you are viewing the tool in this particular plane. ZO, XO. So this particular angle is your gamma naught or orthogonal rake angle, and this particular angle here is alpha naught or the clearance angle in the orthogonal plane. So this is for the principal cutting edge. You have another cutting edge here, that is the auxiliary cutting edge. So same, if you draw another orthogonal plane, say ZO, for auxiliary I am writing A, okay. Similarly, this is XO A. This is perpendicular. So here also you will be able to get a cross section like this, cross section of the tool, and this particular angle here is your alpha naught A. Okay. So I'm denoting it as alpha naught A. This is the this is the flank angle of the auxiliary cutting edge on the orthogonal plane for the auxiliary cutting edge. So this is the orthogonal plane for the principal cutting edge, pi O. So I'm writing P here for the principal cutting edge, and this section here, it has been drawn on pi O for auxiliary cutting edge. Okay, I hope it is pretty much understandable. So what are the other two angles here? So suppose this is that X direction on the, this is the base plane. This blue color what I have drawn here, no, this entire thing is the base plane. Okay. So on the base plane, if you visualize the tool, so this particular angle that the principal cutting edge makes with the longitudinal axis. See, this is not actually the principal cutting edge. It is the projection of the principal cutting edge on the base plane. Okay. So the angle that it makes with the longitudinal direction, that is denoted by the principal cutting edge angle phi, and this auxiliary cutting edge, the projection of the auxiliary cutting edge also makes an angle with this x, that is longitudinal direction, that is phi 1. We are denoting it by phi 1. So that is the auxiliary cutting edge angle. So this is phi 1, and the next, the second last denomination here is phi. The last one is r, or the nose radius in millimeter. So this is the tool signature for ORS. Similarly, you have for ASA, NRS, MRS. You have to get yourself familiar with these different tool signature systems, and also how to convert from ORS to ASA or from ASA to ORS. Similarly, from ORS to NRS or vice versa, and from ORS to MRS and vice versa. We deviated from the question a little bit to get this basics clear. Now, getting back to the question, in case the angle in the above tool given as 5 degrees, so 5 degrees is basically inclination angle. What is inclination angle? If we draw a perpendicular to the projection of the principal cutting edge, sorry, excuse me, this is perpendicular to this axis here. Now if you try to visualize the tool from here, from this direction, say your eye is fixed here and you are trying to visualize the tool on the cutting plane. Your cutting plane contains this principal cutting edge. Okay, so if you visualize your tool there, you will be able to see something like this. So this particular angle here is your inclination angle lambda. So this will be the case for positive value of inclination angle, and in case you have a negative inclination angle, then it will be like this. Okay, so this is for negative inclination angle, and this axis is nothing but z naught. Mind you, this axis is not this particular axis. Okay, this axis is for the projection that I have drawn on the cutting plane. If you try to visualize on this base plane, then this axis is YO, and similarly this axis is XO. But if you take the cross section of the tool and visualize in this orthogonal plane or the cutting plane, then this particular axis will turn into ZO, and this similarly this will also turn into ZO, and this will be YO. Okay. Okay, the question says that in case the angle in the above tool that is given as 5 degree, that is this inclination angle, here 5 degree means it is a positive inclination angle, tool is inclined in this manner from this base plane. Okay. So the scenario is like this. Yeah. If it is being changed to 0 degree, then the following change will happen in the machining process. So what are the options given? The chip will flow perpendicular to the workpiece. Chip will flow perpendicular to the workpiece. Cutting force required will be less. Cutting force, yeah, okay. So what is the purpose of giving this lambda? Anyone? Why do we prefer to give a positive? See, this will also act as a rake angle. Although we define it as an inclination angle, it is also a rake angle, that is defining the rake surface in a given plane, that is the cutting plane. Just as you have a rake angle on the orthogonal plane, so these angles which are associated with the rake surface of the tool, we name them as rake angles. On the orthogonal plane, we name it as orthogonal rake angle. On the longitudinal plane, we longitudinal means xz plane, we name it as back rake angle, and on the other transverse plane, we name it as side rake angle, right? So these are the different terms. Similarly, inclination angle is also a type of angle which is associated with the rake surface. So we are visualizing it on the cutting plane. So We give this positive value of rake angle to allow the chip to flow easily. That is the first thing. Second of all, the cutting forces will also reduce. If your chip is able to flow easily, first of all, your tool will be able to make contact with the workpiece at an angle. So, this due to this angle of attack, you will get your forces reduced. If the tool would have attacked the workpiece like this, then the forces required for cutting would have been higher. So you are attacking the workpiece like this. So this angle, it is called that inclination angle. So if this inclination angle of 5 degrees was not present, if it would have been a zero inclined rake surface, then the cutting forces required will be less. This would have been wrong. This option is wrong. Rather, it should have been higher. The chips will easily flow out of the working zone. Again, this is the wrong option because we are providing this positive value of rake angle to allow the chips. Yeah, it reduces cutting force. See, a positive value of rake angle reduces cutting force. Okay. If you are giving a positive value of rake angle, then it will reduce cutting force. But here, what you are doing, you are from 5 degree, you are reducing it to 0 degree, right? You are not increasing the this particular rake angle or inclination angle. Rather, you are decreasing it. For negative rake, your surface would have been like this. Okay, so this would have been negative rake. Downwards, it is positive rake. Okay, so what you are doing, you are reducing from 5 degree to 0 degree. So your cutting forces will increase. The chip flow will be hindered. Hindered as in they won't be able to flow out as smoothly as it would have been in case of a higher value of rake angle, a higher value of positive rake angle. Power consumption of the process increases. So D is a correct answer because yeah, because you are increasing the rake angle. So sorry, you are decreasing the rake angle or inclination angle. So power consumption of the process should increase. Chips will flow parallel to the workpiece. I'm not sure about option A because if you try to visualize it in another plane, say chips will flow parallel to the workpiece. I think it should have been perpendicular to the workpiece, not parallel. Like the chip flow would have been like this in case lambda is 0. So it's essentially perpendicular to this particular line. In case you have a positive rake angle, your chip will deviate away from this particular line. So this will be the case for positive rake angle. So that is more favorable, right? You want this particular phenomenon. Suppose you give a negative rake angle in this particular direction. If you give a negative rake angle, then your chip flow will be more towards the machine surface. This is the machine surface. Your chip will flow more towards it. Sorry, the chip flow will be deviated more towards the machine surface. That is unfavorable. However, if you give a positive rake angle, it will deviate away from the machine surface. So that is more favorable. And for lambda is equal to 0, it will be perpendicular to the workpiece, we may say. So I don't think it will be parallel to the workpiece. Rather, it should be perpendicular to the workpiece. So A is also wrong. So option D is correct. Your power consumption will increase. Okay. Coming down to the third question. The cutting force and the thrust force in an orthogonal cutting. So these particular terms are important. Orthogonal cutting operation. So you must be familiar with these two terms, orthogonal cutting and oblique cutting. What is the difference between orthogonal and oblique cutting? Anyone? What is the fundamental difference between orthogonal cutting and oblique cutting? Yeah, 90-degree means like, please elaborate. You can unmute yourself and answer.
Hello.
Yeah, Kriti, go on.
Yes, sir. Sir, in orthogonal, the angle is generally made 90 degrees.
Which angle? Which angle are you talking about?
Sir, in
Uh, like which angle should be 90 degree?
sir, inclination.
No, in orthogonal cutting operation, your inclination angle is 0 degree. So say this is your tool. This is the cutting edge of the tool, and this is the workpiece. Sorry. This is the workpiece, and this is the cutting velocity VC. And this particular part is the chip. This is the chip flow. VF I am denoting. So your workpiece is either the tool is coming like this. Say in shaping operation, the tool is moving with respect, like there is a relative motion between the tool and the workpiece. But in case of shaping operations, you have the tool moving. In case of turning operations, you have the workpiece moving, right? So this is the simplest visualization of any machining operation. So this is the principal cutting edge. If your principal cutting edge is perpendicular to the direction of the cutting velocity, then it is called as orthogonal cutting. So essentially the chip flow will also be perpendicular to this principal cutting edge. So here lambda is 0. However, if you incline the tool a little bit, say like this, so in this case also the cutting velocity is like this, and but in this case the sorry, so this is VC. So this was the original principal cutting edge here. This is same as that. However, here the cutting edge of the tool is inclined to this particular line. So in this particular angle is called lambda. So here we can't write VC is perpendicular to PC. We can't write this. Rather, this we can say that VC makes an angle with principal cutting edge. What will be the angle between VC and principal cutting edge here? It will be 90 minus lambda, right? So how can I show this? So I draw parallel to this principal cutting edge here. Then, by the way, all of these angles I am drawing in this particular plane. Okay. Here also in this particular plane, base plane rather. So VC and this particular principal cutting edge makes an angle of 90 degree. This is 90 degree plus lambda. Is it clear? So your cutting velocity here doesn't make an angle of 90 degree with principal cutting edge. Or the motion of the relative motion between the tool and the workpiece is that direction of that motion is not perpendicular to the principal cutting edge. It is inclined by an angle that is known as inclination angle. Okay, so this type of cutting we call as oblique cutting. Here lambda is not equal to 0. This is orthogonal cutting where lambda is equal to 0. So this is the basic difference between orthogonal cutting and oblique cutting. So this Merchant circle diagram and all, is it like valid for orthogonal cutting or oblique cutting? Merchant circle diagram, is it valid? It is valid for which type of cutting? Sorry. So it's valid for orthogonal cutting. Yeah, right. So if you are asked to evaluate the forces in case of oblique cutting, like there you need to convert the system of forces into another plane. So I'm not going into that complexity. It is generally being taught in like the final year of BTech or say in master's level. So there we do some transformation from fx, fy, fz to fm and o we denote as like in the inclined system, say in NRS system, their NRS system becomes like normal rake system. ORS means orthogonal rake system. In case of normal rake system, we define one normal plane which is inclined at an angle. So it is perpendicular to the cutting edge. Okay, that normal plane is perpendicular to the cutting edge, and there if we say that lambda is not equal to 0, then you will then there will be a variation in the forces. Like the forces for lambda equal to 0 will be different, and if you are having lambda not equal to 0, the forces will be different. So accordingly, we make the transformation. So I'm not going into that depth. Rather, coming back to this particular question, it is pretty easy question. So I will try to solve it using Merchant circle diagram. Why? You see, if you remember the particular equations, then also you will be able to solve. But it is not possible to remember all the equations for all the forces, right? So in that condition, it's better to draw the Merchant circle diagram. It won't take time, believe me. Like if you are new to this, then initially like you will take some time to understand and draw the Merchant circle diagram. But once you practice good number of problems on this dynamics of machining, then it it won't be like difficult. It will be easy rather. So we are given with the cutting force and the thrust force here, as Fc is equal to 1470 Newton and Ft is equal to 1589 Newton. The rake angle has been given as 50 degrees. So sorry, it won't be 50, it will be 5. So 50-degree rake angle, it's like huge. You won't be able to incorporate that, right? But then the tool, see, you can't make your tool like this. It will become very, weak. This would be 45 degree, 50 degree will be more, say like this. So this is not suitable for machining also. This type of tool. So it will be 5 degree. That is a more plausible value. So your this rake angle, if it's generally mentioned as rake angle, you have to assume that it's orthogonal rake angle. Okay, 5 degree width of the cut. So this particular diagram should be there in your heart while you're solving these machining problems. So what is this angle? This is my tool. Okay, and I am viewing this entire thing on orthogonal plane. Okay, so this angle will be orthogonal rake angle. This angle will be orthogonal clearance angle, although it's not required here, and still I am just mentioning it. What will be this angle? So you see a plane here, right? So this is the plane along which the shearing will occur. Shearing means the material will get plastically deformed due to the action of the tool, and it will get separated out or severed out, and due to this plastic deformation, the the separation of the material occurs along this particular plane, and the rest of the material gets flown away in the form of chip. So this is the chip. So this particular plane is known as shear plane. I hope you are familiar with this. And the angle that the shear plane makes with this particular direction, or the cutting velocity direction rather, that is called beta naught or shear angle, shear plane angle. You can call it as shear plane angle. That is beta naught. Okay. So if you this I have drawn in 2D. If you draw it in 3D, you have a width associated with this particular plane. So in 3D, your plane will look like this. So this will be the width of the cut. This is the width of the cut, and this is your shear plane. So this, like, if you look into the depth of this particular diagram, then you will get to see this. Okay. Now it has been said that W is equal to 5 mm. Width of the cut is 5 mm. Uncut chip thickness. This is the uncut chip thickness. A1. Before getting cut, the thickness will be A1. So that is given as 0.6 mm. Uncut chip thickness. After the chip has formed, we call it as just chip thickness. Before getting separated out as a chip, this particular thickness we call it as uncut chip thickness. This particular thing you can't measure out directly. What is in your hands while you are doing a turning operation? What are the input parameters? You give a particular speed, spindle speed, that is, say, the workpiece speed, that say it's n RPM. You give a depth of cut and you give a feed. So this A1 and other parameters, like you will see another parameter, this W rather. So these are related to S naught, that is feed and depth of cut, by some equations. This we have discussed in the last video lecture, if I remember correctly, in the last live session. So yeah, chip thickness ratio R, it is given as 0.38. The shear strength of the work material, so you have to find out tau s. Okay, so your approach should be like this. So what are the required parameters to find out tau s? You have to find the shear force divided by the shear area. So this shaded region is shear area. Okay. So what will be AS? Anyone? How do we calculate AS? You have the entire picture here in this particular diagram. You have to find out AS. It's W into A1 by sine beta naught. So it's basically this particular side, this particular side into this side. So if you see in this diagram, it's just this particular edge here into W. So this you can calculate from, like, A1 is this one and this is beta naught. So this is nothing but A1 by beta naught. In this triangle, if you focus, you will get this A1 by beta naught as this particular dimension into W will give you the shear area. Okay, so this you can directly calculate. 5 into A1 is 0.6. Okay, so beta naught you don't know. So how do you calculate beta naught? You have this particular equation, right? You're given with R, so tan beta naught to R cos correct me if I am wrong. This particular equation, this is correct, right? This equation. Okay, so from here you will get beta naught as, so you know all the values here, right? Tan inverse of R is 0.38 into cos 5 degree divided by 1 minus 0.38 into sine 5 degree. What is this coming? Oh, what is the value that we are getting from here, beta naught? Can you just calculate and tell me? Coming out as 21.38 degree. Okay. This shear area will be somewhere around 8.23 millimeters square. Okay. Which is a very small value. Yeah, right. 21.335. Okay. Still, I haven't left any space for drawing the merchant circle. I think you have noted down these values. What I will do is I will just erase this. Anyway, it will be there since I'm recording the video. I will draw the merchant circle now. I hope it is clear till this point. It's a small calculation. I'm just elaborating it for the ease of understanding. That's it. 8.33 mm square. Oh, you have to remember this value. So now you have to calculate Fs. So for that, you will take help of merchant circle diagram. So this is your tool. This is your shear plane. This is your chip. You draw a perpendicular here, another in this direction, and this angle will be your gamma naught. Now, this is the rake surface, right? So if you project it downwards, then the friction force will be along this rake surface. So this is nothing but F. F is friction force. Normal force will be perpendicular to friction force. Say this is N. By the way, I don't think this is required. This F and N is not required in this particular problem. You can directly jump to the other angles. So just for the ease of understanding, I drew these two particular angles. So this will be resultant, and this angle is nothing but eta, friction angle rather, which is tan mu. Sorry, tan inverse mu. Mu is F by N. Okay. So this particular angle is not required. I am just erasing it. Otherwise, it will cause confusion. Now, what is this force? This force is a cutting force. Perpendicular to it, we have the thrust force. You can also denote it by Fz because this force is acting in z direction, and this as xy. This is acting in the xy plane. Anyway, you can denote it by any of these two, and the resultant of this will be R. Similarly, you have the shear force here. Fs, and perpendicular to the shear force, you have the normal force Fn. See, this normal force is not the normal force that is acting on the rake face. It is the normal force that is acting on the workpiece on the shear plane. Okay. So don't confuse this with the normal force that is acting on the radius. So now simply if you draw a circle joining all these intersection points and keeping this r as the radius, sorry, diameter, then you will arrive at this Martian circle. Sorry, I'm not able to draw a proper circle here. Anyway, now if you carefully see this diagram, we'll know that this is beta naught. This angle is beta naught, right? You can stop me if you're unable to understand any particular point. Okay, so this is beta naught, and okay, so can do one thing. So you're given with FC and FT, you have to find out FS. You're given with FC and FT, you have to find out FS. So you focus on this particular line. Okay. Somehow, I'm just removing this FN line. Somehow, if we could draw the projection of this FC on this particular line, this line along FS, this is the line along FS. So up to this point is your Fs. So if we could draw a projection of this Fc on this Fs, and similarly on the projection of this Ft on Fs, then we will be left out with Fs. So it's easy. Like, you just have to find out the projection. So this is your Fs. This is your Fc. And this is your Ft. This is your R. Anyway, you don't need R here. So along this line, if you drop a perpendicular, similarly you drop another perpendicular, then you can write. By the way, what is this? This angle is beta naught. What is this angle? Preeti, talking. Anyone? Yes, what will be this angle? This angle will also be beta naught, right? How we can say that?
Yes,
See,
sir.
yeah. This is also beta naught. So simply you can write from here that Fs is equal to Fc cos beta naught minus this particular value. What is that? Ft sin beta naught. Okay. See, you have two options. Either you remember this particular expression, or if you have practiced this enough, then you can directly arrive at this particular equation just by looking at the Martian circle diagram. Okay. Now you substitute the values. What will be this Fs? It's 1470 cos 21.38 minus 1589 sin 21.38. Is it coming around 789? Can you just confirm if it's around 789.56 Newton? The value of Fs. I think I've made some mistake here. Yeah, can anyone just confirm, like, what is the value of Fs coming out? Anyway, I'm leaving it till here. It should come around 94 or something like that, 94 megapascal or close to that value. Okay. Around 95, I'm writing it as around 95 MPa. You can just check with the answers. I hope this is clear. Do you have any doubt regarding this? Oh, so there's a second part to this question. What is also the coefficient of friction in the operation is? How do you find the coefficient of friction? See, there are three angles. Okay, one is the rake angle, orthogonal rake angle. Rather, one is the shear plane angle, and the third is the friction angle. Which are these are the three angles which are associated with the Marchand circle diagram. In this particular problem, you have two angles as known, and that is beta naught and gamma naught. You have to find out eta. So there are two most popular equations which relate these three angles. One is Lee-Shapper's equation. So what is Lee-Shapper's equation, and like what is it based on? So the another what is the other equation? It's the other expression is Ernst and Marchand's equation, Ernst and Marchand's formula. So both of these are based on like minimization of the cutting energy, the energy which is involved in cutting. So the shearing will occur along that plane only, where the power required for cutting or power required for shearing will be minimum. So going by that, and then differentiating and a couple of more, rearrangements, we arrive at Ernst and Marchand's equation, which goes by, wait. This is Ernst and Marchand's equation, and Lee-Shapper's equation. It is more realistic because here we take into account the dynamic nature of the strength of the material. Like shear strength of the material is not constant as tau is, rather it is varying due to the dynamic nature of this deformation that is occurring during the machining operation. So from there we get beta naught plus eta minus gamma naught as pi by 4. So going by this formula, since it is more realistic, we can calculate eta. It's 45 degree minus beta naught is 21.38 plus 5. Close to 28.62 degree. From here, mu is equal to tan of this particular angle, fixed angle, will be around 0.54. Okay, so now one thing, the value that we get here, this mu is equal to 0.54 from this Lee-Shapper's expression. That is the apparent coefficient of friction. That is not the actual coefficient of friction. Okay. So we have discussed earlier that the chip that is flowing. So first of all, like if the cutting is not orthogonal cutting, if it's oblique cutting, then the deviation will come. One deviation will come in this mu. So that is one factor. So this mu is the apparent coefficient of friction. Now, and if you use the Ernst and Marchand's equation, then what will be the value you will be getting for mu? If you use this expression, 1.382 coming around 1.3. So this, you see a deviation here. These two answers are like not close. So generally we follow Lee Shaffer's expression, but since in this question it's not mentioned explicitly, so you can write that taking into account Lee Shaffer's expression or like assumption, you are using this particular formula and you are arriving at this value, or the other way around. If you're using Einstein-Martin's formula, then you can proceed accordingly and mention that. A couple of theoretical questions and it will be over, I think. Okay, we have another numerical here. So let's complete that first. Turning is performed on a work material with shear strength of 250 MPa. So you're given, so in the previous problem, you have been asked the shear strength of a material. You are given an unknown material, but you know the cutting forces that is coming. You might have measured that using some dynamometer. Then for that unknown material, you are trying to evaluate the strength, that is the shear strength of the material. That is one type of problem. In realistic scenario, I'm just speaking. Another type of problem will be, you are given with the material which is known to you. So as an engineer, you have to predict the forces that will be acting on the tool and then design the tool accordingly. So this problem is like of that sort, whereby you are given a known material with a known value of shear strength rather. It's 250 MPa. The cutting speed, feed, and the depth of cut was 3 meter per second. A rake angle has been given as 7 degree in the direction of chip flow. So what is in the direction of chip flow? Why it is mentioned here? Any guess? Already it is written using the orthogonal model. So a couple of minutes back I said that if you have a zero inclination angle, the chip flow will occur perpendicular to the principal cut, like perpendicular to this projection of the principal cutting edge on the base plane. Okay. So this is also, and yeah, in this case you also have to assume another thing. Some amount, like if you zoom into this portion, it will actually look like this. Okay, this is the nose radius. So you also have a nose radius effect, that from like the material which is getting intercepted here, for that the chip flow will be occurring in this direction, and which is getting intercepted here, for that chip flow will occur in this direction. So you take a weighted average and you get a resultant chip flow in this direction. But I'm not going into that complexity. I'm just assuming that the nose radius is 0 here, and hence the chip flow is just occurring perpendicular to the principal cutting edge, that is this particular edge only. This particular edge only. So this is VC, and the angle that is measured along this direction, it has been mentioned as 7 degrees. So if you view in this particular plane here, I'm not cutting it, I'm just saying that if you view in this plane here, you will get to see something like this. So this angle is the orthogonal rake angle, and this is the orthogonal plane. Okay, and this plane here, it will be the, which contains the cutting edge, it is the pi c, or the cutting plane. That's it. So the resulting chip thickness ratio R is 0.5. Using the orthogonal model as an approximation, the shear force in Newton. Okay. So in the previous problem, I already showed this diagram, right? I'm not drawing the tool again, I'm just drawing the shear plane here. So this is W. This is uncut chip thickness A1. And this little angle here is beta naught, or the shear angle. So all you have to find out is AS, right? Because we know that tau s equal to Fs by AS. You are being asked Fs. All you have to calculate is AS. So AS is W into A1 by sine beta naught. So I told you that this A1 and W are related to the input parameters, speed and depth of cut, and we already discussed it in the last class, I think. So okay. Sorry, should be this. You're encouraged to remember this two particular expressions. It's easy, or you can directly remember it in this form. Like this product will not have effect of this sine phi. So you can directly write this as S naught into D, that is depth of cut, divided by sine beta. Okay, so this W into A1 is same as S naught into D, because this sine phi will get cancelled out. Okay. Okay, now just calculate this. How much is it coming? S naught is 0.2, so depth is 3, that's 0.6. Okay, you also have to calculate beta naught. So tan beta naught is gamma naught divided by 1 minus r sine gamma naught. That's 0.5 into cos 7 degree divided by 1 minus 0.5 into sine of 7 degree. And 27.8 degrees. Correct me if I am wrong. Is it correct, Preeti and Tawkir? I hope that you are following the numericals. Okay. Yeah, Tawkir. Do you have any doubt? Okay. So it's 27.8 degrees. Now just simply substitute the values. Be careful with the units. Here it's given in millimeter per revolution. It may be given in millimeter per minute, and RPM might have been given. So in that case, you have to divide it by RPM to get millimeter per revolution. Okay. So be careful with all those things. This is coming out to be 1.284, I guess, millimeter square. Okay. Therefore, Fs is 250. That's Newton per millimeter square. That is MPa into coming around 321.1. 321 just a minute. Yeah. Is you're also getting this answer? Just confirm for me. You have been asked to round off to the nearest integer, so it's 321. You're also getting the same answer? Okay. Yeah. Last question is which among the following is not an assumption of merchant's first relationship? So this is an important question because you need to know what are the assumptions that you have considered for orthogonal turning. So first assumption is orthogonal turning. So in which cases you can apply this merchant circle diagram, and in which problems you can't apply the merchant circle diagram. But you need to know that. So the cutting edge is perpendicular to the cutting velocity. So that is the condition for orthogonal cutting, right? This is cutting velocity and this is principal cutting edge. If this is 90 degrees, then it is orthogonal. If it's inclined by some angle, we'll say lambda, then it is called oblique. So you can apply merchant circle relationship or merchant circle diagram or merchant's first relationship only in case of orthogonal cutting. So this is not the correct answer. Then coefficient of friction is constant. Tool, acha, okay, let's eliminate the correct, like what are the correct assumptions? Let's eliminate that. Tool nose radius is 0. Yeah, this is also an assumption because I told you that due to this nose radius, there will be a deflection in the chip. Okay. So that is popularly known as the nose radius effect. Originally, the chip should have been in this direction. Sorry, but due to this finite value of nose radius and also the this cutting edge angle, this is also changing, right? So at this point, you have an angle equal to this much. At this point, the angle is this much. It has changed from here to here. So it's decreasing in this manner. So from 0 to 5, it's increasing, okay, from here to here. That we call as nose radius effect. I'm not getting into the details. You can also quantify that. That is the chip flow, the deviation in chip flow due to this nose radius effect. You can quantify that. So this is our correct assumption. Workpiece material is rigid and perfectly plastic. Yeah, you're not considering the elasticity of the object. That is important because if the deformation would have been elastic, there would have been some recovery, and the stresses associated it would have been different. The deformation takes place in a thin zone. Okay, so the deformation it is associated with a thin zone. So yeah, your depth of cut it shouldn't be pretty high. So that so this uncut chip thickness should be low enough. And like if you want to correctly explain this, then you can go by this, like the deformation takes place in a thin zone. Okay, so this is your tool here. This particular zone where the deformation is occurring, this section, so if see this plane that I am showing here now, that is having a finite thickness in actual regime. In actual, this plane is just like a plane is such an entity which is not having any finite thickness, right? It should have it should be having ideally having zero thickness, but yeah, but in actual it is having a finite. This zone is having a finite thickness. In Merchant circle diagram, we are not considering that. So the stress can this maximum stress is occurring. It can be anywhere around this zone. It may not be along this plane itself. So that's why you're considering that this deformation takes place in a thin zone. Thin. So this is also correct assumption. A continuous chip with built-up edge. Okay, another thing is coefficient of friction is constant. Yeah, that you have to consider because on the rake surface, we know that many phenomena is taking place together. The chip is gliding on the rake surface, which itself is a dynamic phenomenon. Then built-up edge is forming. Then like you can have some coating on the tool that is getting worn off. So because of that the mu can change, but when you're drawing the merchant circle diagram, you are not considering this f to be changing. F and n are constant values here, so that's why the eta is also constant. So friction coefficient we consider to be constant. Continuous chip with built up edge, so this is a incorrect assumption, okay, or rather the correct option here. So if we consider built up edge, then you're already, so this is my tool tip. This is my tool tip. So if your built up edge is already occurring here, then the rake angle should be not this value. It should be rather this value. This small angle should be rake angle. So due to built up edges, we see that the rake angle is changing, tool chattering is happening, all those dynamic things are happening. So you can't. So this is not an assumption. Rather, you have to nullify the fact that built up edge is forming. So this is this is not a correct assumption. For better surface finish, the tool has to be sharp. Rake angle should be relatively higher. Feed rate has to be large. This is wrong answer, wrong option. Because if you increase the feed rate, you can. So you have another derivation here. I'm not going into that. Suppose this is the position of the tool at T1. This is the position of the tool at T2, like time 1 and time 2. So you have fed the tool in this direction S0. After one revolution, this tool has moved from position 1 to position 2. So this is basically the feed rate, right? S0 is the distance from here to here in one revolution time span. So by the time the workpiece has rotated by one revolution, the tool has moved from here to here. So that is only S0. So you can calculate that this height here, if you take this section, so the finished surface that you are getting is not a plane surface, rather it is having undulations like this. So this particular height you can quantify from these angles and this S0 value. You know this auxiliary cutting edge angle, you know this principal cutting edge angle, this one and this one, and you also know this S0. So from there you can calculate this HM. HM is a parameter by which you can evaluate the roughness of the surface. So higher the value of S0, higher will be HM, right? And also the roughness will be more. So your feed rate should be small to get a better finish. In practical also, I think you have visualized this. If you increase the feed rate, the surface you are getting, it's not good. Rake angle should be low. This is also incorrect. So if you are providing a larger positive rake angle, then your chip flow will be more smooth, and also the chances of the chips interfering with the finished surface, it will also be less, because you are providing a smoother path for the chip to flow away. So rake angle should be sufficiently high, but at the same time you have to take care that if you are increasing the rake angle, the tool is also getting thinner and thinner. So the tool is getting weak as you are increasing the rake angle. So you have to like optimize this particular rake angle to such a value that your tool is also not weak. It's not weak enough to perform the machining operation without failure, but at the same time, it allows the smooth flow of the chips. So rake angle should be relatively higher for better surface finish. Tool has to be sharp. It need not be correct option because to provide a nose radius, it allows the chip to flow smoothly, and also it prevents the breakage of the tool tip. Okay. Okay. This is the last question for today's session. This numerical. Machining is performed with a tool at 0 degree take angle. So gamma is 0 degree. The shear plane is at 45 degree. The value of shear strain. So, are you familiar with the expression of shear strain? So, I am just directly writing it. I am not deriving it. It has a derivation, but I am not going to the derivation. So, just directly writing the formula here. Yeah, this is the correct expression. I was getting confused about this cot and tan here. So see, in this case, it doesn't make any difference because this gamma naught is given 0 and beta naught is 45 degree. So tan 45 degree, cot 45 degree are equal. So it's 1 plus 1 is equal to 2. Now, so this is the shear strain. Shear strain, if you want to visualize, then say this is your shear plane angle beta naught. Okay. So initially, say like if the machining had not occurred, then this would have been the actual surface of the workpiece, right? And due to the machining, what has happened is, suppose I mark a point here. So this point has, sorry, so this point has traveled up to here. Yeah, you have any question? Like,
No, sir.
okay, so yeah, this point say P has traveled up to here due to the action of the tool, due to the cutting action of the tool. This point P has like it has moved from like point P to say point Q due to the action of the tool, right? So if you drop a perpendicular from this point to here, then basically this distance, say I'm mentioning it as x divided by this perpendicular, say y, will give you the shear strain, basically x by y. So this is the basic, concept behind this derivation. Now if you substitute the angles, and it's easy, like you don't have to do much. So this angle is gamma naught, this angle is beta naught, so you will get another angle which is gamma naught plus beta naught, and by substituting all the values, this is the perpendicular that I was talking about here. So this shear strain, I hope that you know. So this is the material after applying force about this point. This position has moved to this position. The material has moved from point P here to point Q here. Then we can say that this distance by this distance is shear strain. Same thing we have done here. The material has moved from point P to point Q due to this machining operation, and hence this P to Q divided by the perpendicular about this point we are considering as the fixed point here. This is the interface of the tool with the workpiece. So we are considering that to be the pivot about which the P has moved from point P has moved to point Q about this particular point due to this tool. So from there we are calculating this shear strain. You try out this particular derivation, like you try to calculate x, and like x will be this distance. I'm just giving a small hint here. This distance plus this distance. So you try to find out this angle. Try to find out this angle is anyway known, it's beta naught. So you can directly write tan beta naught is equal to y by, say this is x1 and this is x2. So y by x2. Similarly, this angle, I think you have to calculate it. I'm not. Okay, it's just beta naught minus this gamma naught. So how you are getting that? Just let me show it in short. In this particular triangle, this is beta naught. So beta naught. It will take some time. I will encourage you to go through this particular derivation from any standard book. Just try to find out this x1 value here. It isn't difficult, but I'm not able to capture the particular angle here, because this angle will be beta naught minus gamma naught, and you can directly write x1 tan beta naught is equal to x1 divided by y. So x1 plus x2, which is equal to x, will be nothing but y tan beta naught plus y tan beta naught minus gamma naught plus y by tan beta naught. So from here you will get y by tan beta naught, and sorry, uh, So from this and this, I will get this, and divided by y. Shear strain will be x by y. So this y and this y will get cancelled out, and you will be left with tan, like you will be left with this particular equation, tan beta naught plus minus gamma naught plus cot beta naught. Okay. So this is the derivation. I tried to skip that, like how this particular angle is coming out to be beta naught minus gamma naught. You just try it out by yourself. It is not difficult. Okay, so that's it for today's session. I think I've already overshot. So anyway, do you have any doubts from today's session or previous sessions? Shall we close for today? Any yes, no, anything? Okay. Thank you. We will meet again next Friday. I will expect that you just go through the videos for this particular week, and I will frame the questions from those videos only. Okay. Thank you.